Assalamu alaikum and welcome to lecture number 25 of CS 317 Operating Systems. The topic of this lecture is deadlocks and we are using chapter number 7 of the syllabus charts book for this topic. In the previous lecture, we understood what a deadlock is. We realized that there are two types of resources in a computer system. We explored the conditions for deadlock. We listed the approaches to deal with deadlock. We explored deadlock prevention. Deadlock avoidance, technique and algorithm. We have already seen what deadlock prevention is. So the first question is, why shift from prevention? Deadlock prevention algorithms prevent deadlocks by limiting how requests can be made. The limits ensure that at least one of the necessary conditions for deadlock cannot occur. Possible side effects of preventing deadlocks by this method are low device utilization and reduced system throughput. The next question is how to avoid deadlocks. Require additional information about how resources are to be requested. For example, in a system with one tape drive and one printer, the system might need to know that process P will request first the tape drive and then the printer before releasing both resources, whereas process Q will request first the printer and then the tape drive. With knowledge of the complete sequence of requests and releases for each process, the system can decide for each request whether the process should wait in order to avoid a possible future deadlock. For each request, the system considers the resources currently available, the resources currently allocated to each process, and the future requests and releases of each process. Strategy of avoidance. The various algorithms that use this approach differ in the amount and type of information required. The simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. Notice that here the process is not requesting all resources at the start, it is simply declaring its needed resources throughout its lifetime at the start. It will request the same resources later as and when required. Given this a priori information, it is possible to construct an algorithm that ensures that the system will never enter a deadlocked state. A deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that a circular wait condition can never exist. The resource allocation state is defined by the number of available and allocated resources and the maximum demands of the processes. Let us now talk about a major concept in deadlock avoidance called the safe state. Definition: a state is safe if the system can allocate resources to each process up to its maximum in some order and still avoid a deadlock. More formally, a system is in a safe state only if there exists a safe sequence. A sequence of processes P1, P2, all the way to Pn is a safe sequence for the current allocation state if, for each Pi, the resource requests that Pi can still make can be satisfied by the currently available resources plus the resources held by all Pj with j less than I. In simpler words, the resource requests that Pi can still make can be satisfied by the currently available resources plus the resources held by all processes before Pi. If the resources that Pi needs are not immediately available, then Pi can wait until all Pj have finished. Remember, Pj are all the processes before Pi in the safe sequence. Then Pi can obtain all its needed resources, complete its designated task, return its allocated resources, and terminate. When Pi terminates, Pi plus 1 can obtain its needed resources, and so on. If no such sequence exists, then the system state is said to be unsafe. Safe state and deadlock. A safe state is not a deadlocked state. A deadlocked state is an unsafe state. Not all unsafe states are deadlocks. However, an unsafe state may lead to a deadlock. From the figure we can gather that a deadlock state is one of the unsafe states. In deadlock avoidance, we try to keep the machine in the safe state. So in deadlock avoidance, we actually avoid the unsafe states and not the deadlock. As long as the state is safe, the operating system can avoid unsafe and actually deadlocked states. In an unsafe state, the operating system cannot prevent processes from requesting resources in such a way that a deadlock occurs. The behavior of the processes controls the unsafe states, and that is why we do not want our machine to venture into the unsafe zone. So let us take an example system and ask ourselves, is this state safe? A system has 12 magnetic tape drives and 3 processes P0, P1 and P2. P0 requires 10 tape drives. P1 needs 4 tape drives. P2 needs 9 tape drives. At time T0, P0, P1 and P2 hold 5, 2 and 2 tape drives respectively, while 3 are free. Suppose that at T0 we give 2 tape drives to P1. P1 returns 4 tape drives, so 5 are now free. We can give all of them to P0. P0 returns 10 tape drives, so 10 are free now. We can give 7 tape drives to P2. P2 returns 9 and 12 are free now. The safe sequence is P1, P0 and P2. We conclude that the state at time T0 is safe. Note that we have not given any resources to any processes, nor has anyone made a request. We have only computed if a safe sequence exists, and thankfully it does. Can a safe state lead to an unsafe state? Suppose that at time t1, process P2 requests and is allocated one more tape drive. At T1, P0, P1 and P2 hold 5, 2 and 3 tape drives respectively, while 2 are free. Can you compute a safe sequence for T1? Giving the 2 free drives to P1 will satisfy all its needs. P1 returns 4 tape drives. Now 4 are free. These 4 tape drives will not be able to satisfy any other process, and P0 and P1 stay blocked. This is a deadlock. The system is no longer in a safe state. Our mistake was in granting one more tape drive to P2. If we had made P2 wait until either of the other processes had finished and released its resources, we could have avoided the deadlock. A system can go from a safe state to an unsafe state. Now we will talk about deadlock avoidance algorithms. Avoidance algorithms that ensure that the system will never deadlock are algorithms that simply ensure that the system will always remain in a safe state. Initially, the system is in a safe state. Whenever a process requests a resource that is currently available, the system must decide whether the resource can be allocated immediately or whether the process must wait. The request is granted only if the allocation leaves the system in a safe state. In this scheme, if a process requests a resource that is currently available, it may still have to wait. Thus, resource utilization may be lower than it would otherwise be. Deadlock avoidance algorithms. We shall look at two deadlock avoidance algorithms: the resource allocation graph or RAG algorithm and the banker's algorithm. Resource allocation graph algorithm. Limitations and edges. If we have a system with only one instance of each resource type, we can use the RAG algorithm for deadlock avoidance. But if your system has resources with more than one instances, this algorithm will not be applicable. A directed edge Pi to Rj is called a request edge. It signifies that Pi has requested an instance of Rj and is currently waiting for it. A directed edge Rj to Pi is called an assignment edge. It signifies that Pi holds an instance of Rj. A directed dashed edge Pi to Rj is called a claim edge. It signifies that Pi may require an instance of Rj somewhere in the future. Rules. When a process makes a request, its relevant claim edge converts to a request edge. When the request is granted, the relevant request edge converts to an assignment edge. When a process releases a resource after use, the assignment edge converts to a claim edge. This is because the process may repeatedly request the same resource. The resources must be claimed a priori in the system. That is, in the beginning, we only have claim edges. When the process starts, the process needs to declare what resources it will ask for. We can relax this condition by allowing a claim edge to be added to Pi in the graph only if all the edges associated with Pi are claim edges. So if you have a process with some request edges or some assignment edges, then a new claim edge cannot be added to it. But if you have a process with all edges that are claim edges, then this means that it is still in the process of making a claim and you can add a new claim edge. Evaluation of safe state. Suppose PI requests resource RJ by converting its claim edge to a request edge. The request can be granted only if converting the request edge PI to RJ to an assignment edge RJ to PI does not result in the formation of a cycle in the resource allocation graph. We check for safety by using a cycle detection algorithm. Such an algorithm requires an order of n square operations, that is, its own notation is n square, where n is the number of processes in the system. If no cycle exists, then the system will be in a safe state after grant of request. The request is granted and the resource allocation graph changes accordingly. If a cycle is found, then the grant of this request will put the system in an unsafe state. The initial claim edge is restored from PI to RJ. PI is denied the request at this time and it waits. Let us take an example. Suppose that P2 requests R2. So we change the claim edge from P2 to R2 into a request edge from P2 to R2. We have replaced the dashed line with the solid line. Next, we change the request edge to an assignment edge from R2 to P2, assuming that the request is granted. Although R2 is currently free, we cannot allocate it to P2 since this action will create a cycle in the graph. A cycle, as mentioned, indicates that the system is in an unsafe state. If P1 requests R2 and P2 requests R1, then a deadlock will occur. The system state is still the one in the top left corner because we have detected that the next state will be unsafe, so we have rolled back to the previous safe state. We now talk of the second deadlock avoidance algorithm known as the banker's algorithm. About the algorithm. The resource allocation graph algorithm is not applicable to a system with multiple instances of each resource type. The deadlock avoidance algorithm that is applicable to such a system is commonly known as the banker's algorithm. The name was chosen because the algorithm could be used in a banking system to ensure that the bank never allocated its available cash in such a way that it could no longer satisfy the needs of all its customers. Rules. When a new process enters the system, it must declare the maximum number of instances of each resource type that it may need. Again, the process is declaring, not requesting altogether. This number may not exceed the total number of resources in the system. When a user requests a set of resources, the system must determine whether the allocation of these resources will leave the system in a safe state. If it will, the resources are allocated. Otherwise, the process must wait until some other process releases enough resources. Data structures involved. In our system, N is the number of processes and M is the number of resource types. In the Menker's algorithm, these data structures encode the state of the system. Available, which is a vector of order 1 into M. So it's a row vector of order M. Max, allocation and need. All of these are matrices of order n into m. That is, they have n rows and m columns, or as many rows as the number of processes and as many columns as the number of resources. Elaboration of the data structures. Available indicates the number of free resources of each type. If available j equals k, then k instances of rj are available. Max defines the maximum demand of each process. If max ij equals k, then pi may request at most k instances of rj. Allocation defines the number of resources of each type currently allocated to each process. If allocation ij equals k, then pi currently holds k instances of rj. Need indicates the remaining resource needs of each process. If need ij equals k, then pi may need k more instances of rj to complete its task. Note that need was not listed in the original matrices. Actually, need ij is max ij minus allocation ij, or simply put, need is max minus allocation. Let us define the less than equal to relationship between row vectors. Let x and y be vectors of length m. We say that x is less than equal to y if and only if xi is less than equal to yi for all I. If x is 1, 7, 3, 2 and y is 0, 3, 2, 1, then y is less than equal to x. How? Look at their corresponding elements. In y, 0 is less than 1, 3 is less than 7, 2 is less than 3 and 1 is less than 2. So y is less than equal to x. Now x is 1, 7, 3, 2 and y is 4, 8, 4, 2. Let's compare x with y. 1 is less than 4, 7 is less than 8, 3 is less than 4 and 2 is equal to 2. So we can say that x is less than or equal to y. Take x equal to 1, 7, 3, 2 and y equal to 0, 3, 3, 1. Does any relationship hold between them? Take x equal to 1, 7, 3, 2 and y equal to 0, 8, 3, 1. Does any relationship hold between them? Working with rows of a larger matrix. We can treat each row in a matrix as a row vector. We refer to the ith row of allocation and need matrices as allocation I and need I. The vector allocation I specifies the resources currently allocated to Pi. The vector need I specifies the additional resources that Pi may still request to complete its task. Safety algorithm. This algorithm is one of the two algorithms used in Banker's algorithm. This algorithm is for evaluation of safe state. 1. Let work and finish be vectors of length m and n respectively. Initialize work to available and set all finish I to false. 2. Find an index I such that both finish I is false and need I is less than or equal to work. If no such I exists, go to step 4. Step 3. Work equals work plus allocation I. Finish I is true and go to step 2. 4. If finish I equals true for all I, then the system is in a safe state. This algorithm may require an order of m multiplied with n square operations to determine whether a state is safe. Let me remind you that n is the number of processes and m is the number of resource types. Resource request algorithm. This is the second algorithm used in Banker algorithm. This is used to determine if a request can be granted safely. Let request I be the request vector for process I. If request I j is k, then Pi wants k instances of Rj. For request I, these actions are taken. 1. If request I is less than or equal to need I, go to step 2. Otherwise, raise an error condition since the process has exceeded its maximum claim. 2. If request I is less than or equal to available, go to step 3. Otherwise, Pi must wait since the resources are not available or free. 3. Have the system pretend to allocate the requested resources to Pi. So available becomes available minus request I. Allocation I becomes allocation I plus request I, and need I becomes need I minus request I. What we have done here is we have taken the free resources out of available and placed them in the allocation of the process Pi and subtracted them from the need of the process Pi. If the running state is safe, request I is granted to Pi. However, if the new state is unsafe, then Pi must wait for request I and the old state is restored. To illustrate the use of the Banker's algorithm, consider a system with 5 processes P0 through P4 and 3 resource types A, B and C. Resource type A has 10 instances, resource type B has 5 instances, and resource type C has 7 instances. Suppose that at time t equals 0, The following snapshot of the system is taken. P naught holds one instance of B. At a maximum, P naught requires 7 instances of A, 5 instances of B, 3 instances of C. P1 currently holds 2 instances of A. At a maximum, P1 will ask for 3 instances of A, 2 of B, and 2 of C. P2 currently holds 3 instances of A and 2 instances of C, but none of B. At a maximum, P2 will ask for 9 instances of A, none of B, and 2 of C. P3 currently holds 2 instances of A, 1 of B, and 1 of C. At a maximum, it will ask for 2 instances each of A, B, and C. P4 currently holds 2 instances of C, none of A and B. Its maximum claims would be 4 instances of A, 3 of B, and 3 of C. After allocating the resource instances of A, B, and C, I have 3 free instances of A, 3 free instances of B, and 2 instances of C, and this makes my available vector. Compute for each Pi need I. Need I is max I minus allocation I. So 753 minus 010 is 743. 322 minus 200 is 122. 902 minus 302 is 600. 222 minus 211 is 011. And 433 minus 002 is 431. Now we do not need max. We will be working with allocation and need. So this is the system state currently: allocation, need, and available. Run the safety algorithm. Set all finish to false. Set work equal to available. Find an index I such that both finish I is false and need I is less than equal to work. Need 1 is less than equal to work. Work is work plus allocation 1. Work is 332, allocation 1 is 200. So work becomes 532. Finish 1 is true. Again, find an index I such that both finish I is false and need I is less than equal to work. Need 3 is less than equal to work. Work is work plus allocation 3. Work is 532. Allocation 3 is 211. So this becomes 743. Finish 3 is 2. If you have noticed, first when I started scanning, I checked P0, then I checked P1, and I found my conditions true at P1. Then I proceeded from P1 and checked P2, then checked P3, and I found my conditions true at P3. Now I will proceed with P4. Find an index I such that both finish I is false and need I is less than equal to work. Need 4 is less than equal to work. Work is work plus allocation. Work is 743. Allocation is 002. So work becomes 745. Finish 4 is true. Now I will go back to P naught. Find an index I such that both finish I is false and need I is less than or equal to work. Need 0 is less than equal to work. Work is work plus allocation. Work is 745 and allocation of 0 is 010. So work becomes 755 and finish 0 is true. Find an index I such that both finish I is false and need I is less than equal to work. The only candidate left is P2 and it does satisfy our conditions. So need 2 is less than equal to work. Work is work plus allocation 2. 755 is work and allocation 2 is 302. So work becomes 10, 5, 7 and finish 2 becomes true. Now finish I is true for all I. So the state is safe. The safe sequence is P1, P3, P4, P0, P2. You can go back and see through my slides that we have used the same sequence. In this lecture, we understood why deadlock prevention is not a good option. We realized how deadlock avoidance better utilizes system resources. We listed the algorithms for deadlock avoidance. We explored the resource allocation graph algorithm and we explored the banker's algorithm. At the end of the lecture, I ask you to read the book, find the answers to the tasks that I have set you, note your questions relevant to the lecture, and email your suggestions to me. Take care of yourself. Allah Hafiz.